Okay, today we're talking about Chapter 5, Section 2, Logarithmic Functions. We talked about exponential functions in 5.1. Now we're going to talk about logarithmic functions.
Is this 140 pages like last time?
No, I do not think so. I think it's like in the low 20s. Alrighty, so in the previous section, we learned that exponential functions were one-to-one. Okay, and in the previous chapter, we learned that one-to-one functions have inverse functions. Well, logarithmic functions are the inverse of exponential functions. We also learned in the previous chapter, I suppose it was 3.6, that if we were to graph a function that was one-to-one, and in this particular case, let's look at the graph of b to the x, this being the exponential function, then if we were to look at the line y equals x, right, then the inverse of the exponential function will mirror across that line y equals x, and of course we see that here. Okay. We also, I won't get to that just yet, but that's really about it for that. Obviously, we're going to talk more about it, but not here. Okay, sooner or later. Alrighty, so let's actually put this off to the left here, because what I like to do is I like to color coordinate these. Okay, so I'm just going to go with we'll use. Sorry about that. We'll do x. So that was a nice long lull of talking. Actually, I want to put it this way. Like this. Okay. So this is how we go back and forth from logarithm to exponential. I said previously in chapter 5.1 that moving forward, there's really going to be a lot more just moving around as opposed to mindless computation. And this is an example of such, right? So in the previous example, if we had something of the shape this, b to the y, right, is equal to some x, right? In order to change it into logarithmic, all we have to do is say the log base b, and again, I'm color coordinating here, so the bases, right? So phonetically, you would say log base b, right? And of course, that's the same base as the exponential function. And then you would say log base b of x, again, which is what that exponential is equal to. And then it's going to be equal to y, which is going to be my exponent. Okay. As far as I know, there's really no easy way to go about memorizing this. It's just you just do it, and then it'll come natural to you over time. But for the most part, that is the hardest part of the changing, right? It's just memorizing the from one to the other. And that's basically what this definition reads. Obviously, we must have our x has to be greater than 0, or b has to be greater than 0, and b cannot be equal to 1. Because again, well, if x was less than 0, all right, let's look up here. If x was less than 0, well, nothing raised to any power will give you a negative x power, or a negative x value. So that makes sense, right? Furthermore, we haven't talked about it just yet, but that would be contain our domain here. The base has to be greater than 0, which makes sense. Obviously, you might have a negative of it out front, but just talking about b being greater than 0. And b cannot be equal to 1 because, again, 1 raised to anything is going to be 1. So therefore, that's why that's there. And that concludes that. All right. don't suppose, let's see, these steps. Okay. Yeah, so we're not going to follow these steps. We're just going to go and attack this. Like I said, again, you just kind of have to do it, and you memorize it by doing it. Okay, so A, we're wanting to change this from exponential form to logarithmic form. Okay, so they're obviously in exponential form, and we have to put it into log form. So we're going to put log, right? Log, and then the 2 is the base, right? So we're going to say log base 2. And then the argument is what's on the other side of the equal sign. So that's going to be of 8. And that's going to be equal to my exponent, which is 3. Okay. Let's do B. It's going to be log base of 5. Okay, and because that, again, that's the base here. Log base 5 of what? It's going to be of the what's on the other side of the equal sign here. So it's going to be of 1 over 25. And that's going to be equal to my exponent, which is negative 2. And then lastly, we've got log base 1.1 of, it's going to be of z, and that's going to be equal to m. Okay. So again, all I'm doing here is just this, just moving things around, and that's it. Nothing extraordinary here just yet. All right. I think we'll put this on that page, on the current page here. Can we fit it? Yeah, we can fit it. We can fit it down here. Alrighty, now we're going to change from logarithmic to exponential. So here we go. The base, let's put A. The base is right here, so it's going to be a 3 raised to what power? It's going to be the other side. It's going to be 3 raised to the 4th power. And that's equal to 81. Of course, that, we definitely know that to be true, right? 3 to the 4th is indeed 81. B is going to be 4 to the y power is equal to 16. Let's see, does it want to solve it? No. Okay, so we're just going to leave it here. Obviously, we know that y value is going to be 2, right? Because 4 squared is 16. And then C, we got fractions. That's okay, though. It's okay. It's going to be 3/5 raised to the 2nd power, and that's going to be equal to my argument, which is x. All right. So the first two examples are, I won't say the hardest part, but are, if you understand these first two examples through and through, you're going to understand about 60% of the section, which obviously is the majority, right? Because what we're doing is we're just moving things back and forth and solving. And especially when we get to maybe 5.3 or 5.4, whenever we actually do have to solve equations, this will take up most of that computation. So that's good news. Maybe I'll snip this. This seems like it might be good, so let's snip it and check it over real quick. Okay, so because a logarithmic expression represents the exponent of an exponential equation, it is possible to evaluate many logarithms by inspecting or by creating the corresponding exponential equation. There's just some words here, I'll tell you. Remember that the expression log base b of x is the exponent to which b must be raised to in order to get x. Okay, all that good stuff's good. Here we go. For some logarithmic expressions, it is often convenient to create an exponential equation and use the method of relating bases, which I guess, yeah, we talk about in 4.4.5, so I guess that isn't too pertinent right now, right? I mean, what's the point telling us we're going to do something in 2 weeks? Instead, let's just get going. Okay, so really quickly, before we begin this, okay, before we begin this, logarithms create a number. They're actually numbers, okay? Depending on if it's a nice, clean-looking number like A would be, it would be, well, a nice, clean-looking number. So for instance, if I were Sheldon from The Big Bang Theory, I would say, somebody might ask me, hey, how old are you? I would say I am 30. Let's see, I am 31 plus log base 5 of 25. And then the laugh track would hit up, right? Because whoever he's telling how old he is to, they're like, right? Instead of saying, that Sheldon is just 33 years old, he goes a long way and say 31 plus log base 5 of 25. Okay? Because log base 5 of 25, obviously, if you cannot tell, is equal to 2. Right? So let's examine how that is. So for A, you're going to be given problems like this, and you're gonna kind of, you don't have to, but this is what I do. We're gonna write our problem out. Log base 5 of 25. Okay, and then I'm just gonna put is equal to, obviously equal to what, but we are a lot better than that, aren't we? We'll say is equal to x, right? Okay, so then we would rewrite this, and we would say, okay, so 5 raised to the x power is equal to 25. Oh, that's not bad. It's going to be 2, right? So it's going to be 5 is equal to 2. I'm sorry, x is equal to 2. So let's see if I can... We'll just do A and B on this page. So then we would say that x is equal to 2. Okay, and that's that. So now let's do B. Oh, here we got fractions. Here we go. So yeah, it's a good thing we are doing this on multiple pages. So we're going to say log base 3 of 1 over 27 is equal to, again, we're going to say is equal to some x. Okay, well, let's rewrite this in exponential form. We would say 3 raised to the x power is equal to 1 over 27. Well, that doesn't make sense, right? Because 3 to the first is 3, 3 squared is 9, 3 cubed is 27, 3 to the fourth is 81, right? That's true. But what about our negative exponents, right? Well, if 3 cubed is 27, then 3 to the negative 3 must be 1 over 27. Okay, so that's how we do that. And then let's do C. Square roots. Well, they're really trying their hardest, aren't they? Here we go. But we're better than this, though, aren't we? So C, we're going to rewrite this as well. We're going to say, okay, so we're going to say the square root of 2 man, I done lost my concentration. I'm sorry. Oh yeah, what we did was we rewrote the problem first. Right. Okay, so we would say log base square root of 2 of 1/4 is equal to some x. Okay, and then we would rewrite this as the square root of 2 raised to the x power is equal to 1/4. Ooh. Okay, so this looks kind of weird, right? So let's attack this a couple different ways. So we know that 2 raised to the negative 2 power is going to be equal to 1 over 4. Okay, so that's true, but I can't do 1 over this or 2 to the squared negative 2 raised to the negative 2 power, because if I did that, if I did the square root of 2 and I raised it to the negative 2 power, that would be the same thing as saying 1 over the square root of 2 squared, which would just be 1 over 2. Okay, so instead, how do I get this 2 to be a 4? I'm going to have to square it again, right? So instead what I'm going to do is I would say I could raise this to the negative 4th power. Negative 4th power. Right? That would take care of the square root of 2, and then it would square the 2 to get to a 1 over 4. So here we have our x would be equal to negative 4. Okay. Now, actually, I wouldn't say I messed up per se. Instead, what I would do is I would because obviously in the initial problem there is no x's here, right? The x's are just an invention that we have come up with for these problems. But instead, what we do, we would just say, you know, we would put the 2 right here. Not necessarily x is equal to 2. We would just say 2. Okay. So again, we're just kind of inventing a variable here to solve it. Okay. So let me see. I don't think that's abundantly clear. If it is, I'm sorry. I'm going to try and explain it again. You're going to be given this on your homework and test. Okay. There is no x value anywhere on these problems because we invented it because look, there's no x's here. Okay. We did that so we could say, 5 raised to what power, and of course we just invented that x, and we said, well, x is 2. So that in that case, we would say log base 5 of 25 is equal to 2. Okay, so you just put a 2 in there for the blank space. Right, so hopefully that explained it. I'm not going to do it again because I do over-explain things sometimes. Okay, so general properties of logarithms. These are common sense, right? Especially if you know how to do the things that we did on the first page, swapping from exponential to logarithm. They're common sense, and here's why. Let's look at this first one here. Okay, if I were to rewrite that in exponential form, I would say b raised to the first power is equal to b, and that makes sense, right? So again, common sense there, right? And let's look at the second one. B raised to the 0th power is 1, and that also makes sense. Okay, so these are two common sense properties. There are, pretty sure there's 2 more coming soon. They're also common sense, but I don't know. There's nothing else I can really say about that. Yep. So let's proceed. Proceed. All right. So this would be the other part, I guess. And we don't have room. Okay, so we'll just put that with the example. That's fine. Okay, so excuse me. This reads excuse me. Ooh, all right. So this reads, use the properties of logarithms. Use the properties of logarithms to evaluate each expression. Okay, so we could use the properties of logarithms, and there's nothing wrong with doing it, right? But I'll tell you now, I don't go around memorizing these properties. I guess it's just something that's known, right? Again, once you really get familiar with logarithms, you just kind of know. All right. We could equate these to a property, and that's fine. Okay. But let's look at a real quick. Okay. Which one of these properties does it look like? Okay. Well, it looks like number 2, right? It's a log base b of some base raised to the x power. That's equal to x. Okay. And the x therefore would be my exponent there, the 4. So it's equal to 4. So again, I'm just kind of equating these two together. Okay. Now, if I didn't want to memorize these properties, which again I don't. Okay, I don't memorize them. Instead, what I probably would have done here is I would have said, okay, so log base 3, good. 3 raised to what power? Just gonna put an x there. 3 is what power is equal to 3 to the 4th. Okay, well, obviously 3 to the 4th will equal to 3 to the 4th, and so that's why my solution here would still be 4. Okay, so if you don't want to go about memorizing these properties, that's fine. The main thing, like I said, 60% of the fight is this right here. Memorize that, you're good to go. Okay, so that's 4. All right, B. All right, again, heck, I don't know. What property would that be? It's a log base. Again, it doesn't matter. Instead, here's what I'm going to do. I'm going to say, okay, so this is 12 raised to raised to what power is equal to 12? Well, that's easy, right? 12 raised to the first power, so that's going to be equal to 1. Okay, I guess C is where it gets a little. C might be where you might want to memorize something, but you know what? Maybe no. Let's not. Instead, let's it's in exponential form. So let's write it in logarithmic form, okay? So in logarithmic form, it would be log base 7, looks like, right? Because this is the 7 of an exponent. Log base 7 of what, okay? We don't know what. And that's going to be equal to, trying to think if this is actually easier or if I should just go back and show the previous one. Yeah, we'll stick with this right now. Okay, so log base 7 of what is equal to log base 7 of 13. All right, so maybe not. Okay, so let's actually clean that up a little bit. Move it over to the right, to the left. Okay. So again, what I'm going to do here is I'm going to take this, I'm going to rewrite it in exponential or in logarithmic form. So log base 7 of what? Okay, so it would be of, we don't know. It's on the other side, right? It's on the other side. So it's going to be of x. That's going to be equal to the exponent, which my exponent is log base 7 of 13. Okay. So log base 7 of what is equal to log base 7 of 13? Well, obviously, that what would be 13. Okay. So hopefully that makes sense. If it doesn't, this might be one of the rare cases where I think maybe you could, if you wanted to, look at, it's not this page. It is that page. It's not this page. Oh, it'd be this one. Ooh. Would be that property one, right? Which is, something raised to the log base b or of x is equal to x, and of course we see that x is 13. But again, I might have messed up a little bit by stuttering a little too much here, but I really do feel like it's just so much easier if you just remember your exponent to logarithms and logarithms to exponents, as opposed to trying to memorize these other formulas. Because again, these other formulas are just simply common sense. And I'm going to keep C written like that. I'm not actually going to write 13. I'm just going to keep it written like that. That way you can tell where I get the number 13 from, even though I didn't say 13. So C is 13. Okay. All right, now D. All right, D, again, let's rewrite it in exponential form. It's going to be 8 raised to what power is equal to 1. Okay, well, that's easy. It's going to be 0, right? The x value there is going to be 0. And that's that. Okay. So hopefully, let's not put a 0 there. We'll just put 0 here. Boom. Okay. All right. So that was very painful. Sorry. Again, I try to explain too much sometimes. All right, so next we have, excuse me, we have common log and natural log. Okay, the common log, all right, so let's see here. If I were to write the square root of, well, 17, I'll do 16. If I were to write the square root of 16, okay, we know it's a square root, right? Even though we don't write the 2 right here, well, even though we don't write the 2 right there, then we know it's a square root if we don't write it there. If we write anything else there, then we know that it's not a square root. It would be a cube root or a fourth root. Okay, so that's basically what the common log is. The common log, if you just see log all by itself with no base given to you, then we know that that base is going to be a base 10. Okay. Next up, we have the natural log. The natural log is ln of x. Okay, and it's Latin logarithmic naturalis. That's why it's ln instead of nl. But the natural log would be a logarithm with a base of e. Okay, that's all a natural log is. It's a log with the base of e. On previous pages, we had base of 12, base of 3, base of 7, base of 8. Okay, the natural log is with the base of e. Okay, it's just that it's such a special number and it's used so often, it gets its very own notation, the natural log. Okay, whenever I was taking college algebra, I would go log natural every time I wrote it, right? So that's that. this is asking us to, one moment. Alrighty, I think I'm coming down with something. So write each exponential equation as an equation involving a common logarithm or natural logarithm. Okay, so that's not too bad, because we've got first of all, you're going to know if it's common log or natural log, because it'd be natural log if we're using e, common log if we're using 10. Okay, so how would we write e raised to the 0th power is equal to 1? We want to write that in the form of a natural log. Okay, so we would just simply say the natural log of 1 is equal to 0. Okay, because again, the natural log and then the argument's here, and it's going to be equal to my exponent there, which is 0. B, we are going to write this as just as a base of log. Okay, so we're going to say log of, okay, so what's my base? My base is 10 to the negative 2 power, so it's going to be, no, sorry. It's going to be log, there is no, the base again is 10, I'm sorry, I messed up, of 1 over 100, okay? Well, what is log of 1 over 100? Well, that's going to be equal to a negative 2, okay? Again, the reason why is because, let's actually start this over and show where I'm getting things. Okay, so if we were to do this normally, okay, like an example 1 or 2, whichever one took exponentials to logarithmic, we would say log base, alright, the base here is 10 of what? Of my what's on the other side there is 1 over 100, and that's equal to my exponent, which is negative 2. Okay, that's what we'd have done on the first few pages, right? But what we're learning now is that that 10, if it's a 10, it's redundant. We don't have to put the 10, and that's all we're doing there. Okay, C. Okay, so that's e to the k is equal to w. All right, so we're going to say the natural log. Okay, the natural log. Okay, so let's actually start this over. Let's do C differently than we did A. Okay, because sometimes I feel like I don't explain things just right, and you're like, well, how did you get that? Well, here, let's do it this way, okay? Let's do it this way. Let's say log. I know it's a natural log, but I just want to show you. Log of, the base there is e, okay? Log base e of what? What's going to be of w, and that's going to be equal to k, big K, okay? But we learned on the previous page that log base e has its own notation, okay? So that's why we would say, instead of log base e of w, we would just simply say the natural log of w is equal to k. Okay? And that explains how we got a better, I think. Ooh, okay, here we go. More stuff. So again, I mean, this is just moving things around, right? So hopefully, what I said is coming to fruition. It's not much computation. Just move things around. Right? So this reads: write each logarithmic equation as an equation involving an exponent. Easy. All right. So a, what is the base of a? Well, it's log of 10. Okay. So since there is no base given, then we know that the base is 10, and then 10 raised to the first power is equal to my argument, which is 10, and that makes sense. B, this is a natural log, so it's going to be an e raised to what power? It's going to be raised to the z power, and that's equal to 20. And then C, again, no base is given, so it's going to be a 10. 10 raised to the t power is equal to x minus 1. Easy stuff. Okay, now we got to do some evaluation. All right, here we go. Okay, so similar to what we did on the examples. Which one was it? Example 3. Where I put an x in there. We're kind of doing the same thing here. Okay, so we're going to write log of, it's going to be base 10. You don't have to write it though, but it's there. Is equal to 100. I'm sorry, log base 10 of 100 is equal to, what? Okay. Well, if I were to write this in exponential form, I would say 10 raised to what power is equal to 100, right? And then we see that that solution would just be 2. All right, I'm not going to put x equal 2 this time. I'm just going to put 2. And b, again, we're going to have the natural log of the square root of e. Well, that's just ridiculous. All right, and it's going to be equal to what? Okay, so what I would do, let's actually not, let's do this. Yeah, let's do that. Okay, so we can write, and this is actually something we're going to be doing as we move into, and I guess it's 5.4, is changing my exponent, or changing my roots to an exponent. So instead of writing the square root of e, I'm going to write the natural log of e to the 1/2 power. Okay, e to the 1/2 power is indeed the square root of e, so we can proceed there. All right, so the natural log of e raised to the 1/2 power. All right, well, what's that equal to? And well, this one's actually pretty easy. It's going to be 1/2. Okay, because those cancel out with one another. Yeah, that's really it. Okay, and let's do C and D. All right, so it looks like we're going from exponent to natural logs here, and C, maybe I jumped the gun a little bit when I said you don't have to memorize these. And again, and I stand by it. I stand by it that you don't have to memorize it. It's just that, again, whenever you see some base raised to that logarithm and that argument, then you know it's going to be equal to that that argument, which would be x. So in this particular case, this is the natural log, no, the natural log of, I'm sorry, e raised to the natural log of 51. It's an exponent raised to that logarithm, and then so it's just going to be the argument, which is 51. Okay, so according to our cancellation property, right, it would be just simply 51. And then lastly, this is a 10 to the what power is equal to 1. So again, let's see. We can write this log of, again, I'm going to put the 10 even though it's not there. It's going to be equal to what power, or equal to what? And that is 10 to the what power is equal to 1, and therefore we know that my solution would just simply be 0, right? Because anything raised to the 0th power is indeed 1. And real quick, let's actually examine why that is. All right. So why is anything raised to the 0th power equal to 1? All right. Well, let's first of all let's start with 1. How else can we write the number 1? Well, the number 1 can be written as anything over itself. Okay. So let's just go ahead and say x to the y over x to the y. That makes sense. X to the y over x to the y is indeed 1, right? Well, using our exponent rules, we know that I can rewrite this as x to the y minus y, right? It would be the numerator minus the denominator, okay? And then x to the y minus y, well, there, it's y minus y, so that's going to be x to the 0th power. And that's why 1 is equal to anything raised to the 0th power. All right, now we get to sketching, okay? So, in my opinion, this is also really, really easy. And I know I say that about a lot of things. You're probably rolling your eyes right now. All right, but once we got the, where is it at? Here. Once we know the characteristic of how we draw the logarithmic function, which we said was the inverse of our exponential function. Well, once we got that down, it's pretty easy. All right, so this steps for sketching logarithmic functions. We're not going to deal with that just yet. Because again, I don't want to fill your brain with a bunch of stuff. Instead, what we're going to do, maybe we should, let me see if there's any highlights here. All right, so if I want to sketch the logarithmic function of the form log base b of x, okay, again just reading, reading this line here, okay. So what I would want to do, it says start with the graph of the exponential function y is equal to b raised to the x power, labeling several ordered pairs, okay. And then it says because f of x, yeah, all that. No, I got it easier for you. It's easier. It's easier, a lot easier than that. Okay. So here's how it's a lot easier. Let's go ahead and we're going to make a rough sketch here. Okay. All right. So in order to do this, we know we have to remember that the exponential function, if you recall, the exponential function, unless we're doing some sort of horizontal or vertical shift, always passes through that point 0, 1. Okay, so I guess we'll go ahead and do this, whatever. Okay, it always passes at point 0, 1. All right. Well, let's have a dotted line here. All right. All right. So if logarithmic functions are the inverse of exponential functions, then they would be mirrored across that line, y is equal to x. Okay, and of course we're going to see that. So before we do see that, if the exponential function always crosses through the point 0, 1, okay, then I posit that the logarithmic function is always going to pass through the point 1, 0, right? Because that's just on the other side, right? And if I mirror such an equation, it looks something like that. And that's a really good drawing. That's a good sketch of what I'm trying to look for here. Okay. Now, obviously, it does say it says sketch, and whenever you go to do this in your homework, you're going to have more exact points to plot them. But realistically, this is the gist of it, 100%. All right. I'm not cutting any corners, not tricking you here. This is it. Now, if you wanted to, you could obviously do the 3 raised to what power is equal to x. So we'd say, no, we're not gonna do that. I don't like that. This is it. So yeah, again, there we have our rough sketch of it, and maybe we will put that there. It's pretty tiny, isn't it? I will say, I think this is definitely a part where I feel like we should have discussed the anatomy of the logarithmic function before we went about doing a problem like this. Because once we realize what we're looking at and what we're trying to do, it's a lot easier as opposed to just starting right here from ground zero. Okay, so that's what we'll do. It's there, and I'm hoping that we get to that point. I mean, we have to, right? Yeah, there it is. Okay, good. The characteristics, like this, should have went first, in my humble opinion. So this looks like a lot to unwrap, but realistically, you just have to remember they are inverses of one another. They're inverses of the exponential function. Okay, so starting from the top, here we go. All right, so b, our base has to be greater than 0, and it cannot be equal to 1. The logarithmic function with base b is defined by y is equal to, or f of x is equal to log base b of x. Okay, so the domain, I don't know if we actually talked about. Okay, so let's do this. Let's move this to the left because this is very important. When we talked about inverse functions previously in chapter 3, we said that if we have some function f and we have another function, the inverse of f, okay, if the domain, okay, if we were to call domain just some alpha, and the range is some beta, okay, well then the domain of my inverse function is going to be beta, and then my range is going to be alpha, okay, and if you see, they are just opposites of one another, okay. this was a property that we saw on inverse functions in chapter 3. So that's where we see the domain being 0 to infinity, and the range is negative infinity to infinity. Okay, so real quickly, let's look at that real fast. An exponential function, if you recall, goes like this, right? And the domain of an exponential function is negative infinity to infinity, and that's the range of the logarithmic function. The range of the exponential function is 0 to infinity, and that's the domain of my logarithmic function. Okay, so everything that you thought you could forget about inverse functions, well, they're coming back to haunt you, so you shouldn't have forgot about them to begin with, right? So if we have some base greater than 1, again, similar to my exponential function, if we have some base greater than 1, then we're going to have this arc here. Okay, but if our base is between 0 and 1, instead of going up, we're going to be going down. Okay, we see that the graph intersects. We intersect at 1, 0 each time, right? So again, we're just flipping. We're just flipping across. We're just flipping across this line right here. Okay, so instead of crossing at 0, 1, we're going to be crossing at 1, 0. Graph point. Okay, increasing. Okay, the y-axis is our vertical asymptote in both cases, right? So in the function, and of course, obviously the function is 1 to 1 because, well, it is the inverse of the exponential function, and in order to be an inverse, you must be 1 to 1. So that makes sense as well. So I think we unpacked all that pretty well, didn't we? Right. So let's probably go and do some transformations. Yeah, transformations. Okay, so transformations, I don't think they are abundantly hard, especially if you succeeded in I guess section 4 of chapter 3. So we're just going to go ahead and snip all this. Okay, maybe shouldn't have. Nah, it doesn't matter. Okay, so here we go. If we were to look at here, look here. Okay, it looks like we've got a few transformations, right? One of them, here we go, looks like we have a vertical shift. Okay, so we have a vertical shift. Looks like here we have a horizontal shift. Okay, so, and of course we always know that horizontal shifts always go first. Horizontal shift. All right, we have a vertical shift, but that's always going to go last. So let's skip that for right now. And then we have the negative of the parent function, so it's going to be negative of the natural log. And if we take the negative of a function, then you mirror that. Let's see. Mirror across x-axis, max, right? So we're going to mirror it across the x-axis, and then we can do our vertical shift last. Vertical shift last. Okay, and of course we can see that in our solution here. We take the horizontal shift. Okay, that's not the actual one, is it? This would be it. So that was a lot of words to get to this point. Whereas I feel like, let's just cover that. Well, yeah, no, we'll put it over here. Maybe we won't just cover it. We'll put it over here instead. Okay. So we said that we have the horizontal shift. Okay, so we're going to horizontal shift. Oh, here's what we did last time. We would say horizontal shift. It is a +2, so we're going to go left 2. So we're going to go left 2, and a vertical shift down 1. Okay, so that's what we did last time for exponentials. So the landmark that we talk about is always going to be at 1, 0. Okay, so what we're going to do is we would take this and we would shift it to the left 2 units, 1 to 2. Okay, so my new graph would look something like this. Okay, and then from there, what we would do is we would flip it across the x-axis. So instead of it going down, instead of it going up from down right here, we're going to flip it across the x-axis. It's going to look something like this. Okay, so that yellow line, I don't know if it's easy to see. Let's actually do it in red instead. It's going to look something like this. That's horrible. Let's try it again. Better. Okay. And then lastly, we said we have a vertical shift down 1 unit. So that landmark being, again, right here, we're just going to go down 1 unit. So we'll go down, and we're going to go something like this. Um, Again, it looks very contrived. That's mainly because it is. Trying to make it nice and neat. Okay, but of course you see that over here. So that was, and let me actually, since I color coordinated, let's color coordinate it here. Okay, so the first thing we did was the horizontal shift to the left 2 units, and then it looks like the red line was the, what I say, mirror across x. So mirror across x, and then the third was in green. The third one is the vertical shift down 1 unit. Okay. So these colors over here match my colors here. Each step. Okay, I think we might be on to the last example here. And lucky for you, the last example is a doozy. Sorry to say. Okay, so let's go back and read what the previous page said. Alright, so in example 9, we sketched the function and observed that the domain was -2 to infinity. Now, we didn't actually talk about that, did we? No, it just says sketch. Okay, well. Alright, starting here. We don't have to sketch the graph of a logarithmic function to determine the domain. The domain of a logarithmic function consists of all values of x for which the argument of the logarithm is greater than 0. So the argument is this part here. That's the argument. Okay. Let's see. For which all values of x for which the argument of the logarithm is greater than 0. Okay. And that is how we're going to figure out how to find the domain here. So hopefully you remember how to do this. If not, this is going to be a really good refresher. Right? So I know that the argument must be strictly greater than 0. Okay, so if you forgot how to do this from way back in chapter 1, buckle up. Here we go. So if I know that this 2x minus 1 for x plus 3 must be greater than 0. Okay, so what I'm going to have to do is I need to solve each of my numerator and my denominator for 0. Okay, and in doing such, let's actually put that in white. Okay, so in doing this, we see that, so my numerator, if I solve my numerator for 0, I would have x is equal to 1/2, or I'm sorry, x is greater than 1/2. Okay, so x is, no, we're going to solve it for 0. And it's going to be x is equal to 1/2. And then that denominator there would be x is equal to -3. Okay, when x is equal to 1/2, my numerator is 0, and 0 is not greater than 0. Okay, so that makes it a false statement. And when x is equal to -3, -3 plus 3 is 0, and that is not greater than 0. Okay, so if you recall, these are going to be my two walls. Okay, so let's do this. And we're going to have walls at -3 and at 1/2. So this is going to be -3, and this is going to be 1/2. Okay, hopefully it's coming back to you, and hopefully there's not a sense of dread coming over you. Right. So what we did here was we said, okay, so this interval here is from -infinity to -3. This interval is from -3 to 1/2, and this interval is from 1/2 to infinity. Okay, and then we have to get a test point. So my test point, again, is going to have to be inside that that interval. Okay, so the test point here, we're gonna use the test point -4. From here, I said if you have 1 and 0 available, use them. And of course, 0 is available, so we're going to use it. And then over here, we're just going to use 1. Okay, and if you recall, what we had to do was we would take these numbers, plug them in for x, and if this is a true statement, then that interval is in the domain. If it is a false statement, then the interval is not in the domain. Okay. Now, there's not too much computation that needs to be done here, except for getting to the point where is this positive or negative. So let's begin that right now. Okay, so -4. If I plugged in a -4 here, well, 2 times -4 is a -8. -8 minus 9 is a negative number. Okay, so this is a negative number up top. Okay, and then if I -4 plus 3, right? -4 plus 3 is a -1. It's also a negative number. So we'd say a negative. So a negative divided by a negative is a positive number, which we're looking for a number that is indeed positive. So this interval works. Okay. Now let's plug in a 0. We plug in a 0 here. 2 times 0 is 0. 0 minus 1, that's a negative number. 0 plus 3 is 3. That is a positive number. A 0 divided by positive is a negative number, and a negative number is not greater than 0. So therefore, this interval does not work. And lastly, 1. 2 times 1 is 2 minus 1. That's a positive number here. 1 plus 3, that is also a positive number, and a positive divided by a positive is also a positive. So this interval works. Okay, so that's it, right? The domain here would be these two intervals that work. So it's going to be negative infinity to -3 unioned with 1/2 to infinity. Okay, so this is the solution. And okay, so maybe I was like slightly wrong when I said you don't have to do too much computation. This is one of those cases. I'm sorry, right? But hopefully, if you forgot how to do it, you remembered doing just now, or we could go back to section 1.9. We see here section 1.9, and rewatch that video to remember how we did things. Okay. Anyways, that does conclude today's lecture.